So today we're going to talk about inverse trig functions, and we're going to introduce the idea of an inverse trig function by looking at what its graphical significance is. So if you remember back to when we talked about inverses, in order for a function to have an inverse, it must be 1 to 1. And if you remember what 1 to 1 means, it means the function would pass the horizontal line test. So if you look at our sine function, it's periodic, which means it obviously repeats itself. And if I draw a horizontal line anywhere, take a look at this dotted line here in the first picture, it would pass through the function multiple times. And what that means is sine of x does not have an inverse unless we can find a way of just restricting our window or restricting our domain and looking at a piece of it. So if you look at the picture on the right here at the top, this is sine of x, but restricted from negative pi over 2 to pi over 2. So again, sine of x is not 1 to 1. So if I want to find a function or a piece of sine that is 1 to 1, I would have to restrict it to negative pi over 2 to pi over 2. So if I color over this portion of the sine graph there, that now is 1 to 1 and should have an inverse. So then how do I find the inverse of this function here? If you remember, the basic idea of a function and its inverse is the domain of one function becomes the range of the other, and the range of a function becomes the domain of the other. So looking at this piece of the sine graph here, the domain is negative pi over 2 to pi over 2, and the range is negative 1 to 1. So if you look down at this picture here at the bottom of this slide, you'd see this is a graph of the inverse function. If you look, y equals sine to the negative first of x, that's just notation for what we would say sine inverse of x, or the inverse sine function. So look at the domain there. The domain would be negative 1 to 1, which is the range of my sine function, and the range should be negative pi over 2 to pi over 2, which was the domain of my original function. And that's really significant because when we start evaluating, we have to consider where sine inverse is defined, so looking at its domain, or what are the possible outputs, which would be the inputs of sine of x. And it'll make sense here in a second, but notationally, I can either write sine to the negative first of x or sine inverse of x, or another way to write it, and you'll see it as arc sine of x. Both of them mean the same thing, they're just notation for the inverse. So if you look here, sine inverse of sine of x equals x. What that is just a statement about how two functions where their inverses are related. So sine of sine inverse, those are inverse functions, which means they should undo one another. So if you look, sine of sine inverse of x equals x, provided that x is between negative 1 and 1. So the idea here I want you to remember is the possible inputs for sine inverse are negative 1 to 1, and the outputs would be negative pi over 2 to pi over 2. So then if I flip-flop those, if you look at the line below it, sine inverse of sine of x is equal to x as long as I have a value in between negative pi over 2 and pi over 2 for x. So something to consider when we get to evaluating is, in order for me to use this property, that sine of sine inverse of x is whatever the input is, I have to make sure that whatever my x value is either in the domain of what function I'm looking at. If it's not, we'll have to do a little bit of trig to find an equivalent angle or an equivalent input that would give us the same value. Now the same properties and the same approach hold for cosine of x. So what I've already done is put the picture here of cosine of x, but restricted this picture from 0 to pi. So if you look at cosine from 0 to pi only, that is now a 1 to 1 function, or 1 to 1 piece of the cosine graph, which means its inverse should exist. So if I color over just this portion of cosine, the domain of that is 0 to pi, and the range is negative 1 to 1. Now if I want to look at the inverse cosine function, or cosine inverse of x, or arc cosine of x, the domain of one should be the range of the other, and the range of one should be the domain of the other. So the domain of my inverse cosine function should be negative 1 to 1. My range should be 0 to pi. So when we want to evaluate the inverse cosine function, cosine of cosine inverse of x will be x. Those functions will undo one another as long as the x value in this case is in between negative 1 and 1. So the idea there is the domain of cosine inverse is negative 1 to 1, or the output of cosine inverse is between 0 and pi. So when we start evaluating cosine inverse, our output will be angles, so somewhere between 0 and pi, whereas our input will be somewhere between -1 and 1. And that you can see that in the graph there in the domain and range. And then when we want to think about cosine inverse of cosine of x, so those functions will undo each other, so that will be equal to x, just as long as the input of cosine is somewhere between 0 and pi, because cosine inverse is only defined between 0 and pi. And hopefully this will make a little more sense when we start looking at some examples here, but I just want to give you some background information on what the graphs look like, so that when we start graphing it'll make a little more sense, and also why we have to restrict the domain for cosine and what that impact is on cosine inverse. And then if we want to look at the tangent function, tangent is also periodic, but we want to restrict tangent to only between the values -pi/2 and pi/2. If you look at that one period of tangent that's drawn there, I kind of colored over it. The only major difference in the way tangent is restricted is tangent doesn't exist at pi/2 and -pi/2, and the range is -infinity to infinity, which means if I think about the inverse tangent function or arctangent function, the domain would be -infinity to infinity, and the range would be -pi/2 to pi/2, not including those. So those are going to act like horizontal asymptotes for the tangent inverse, which were vertical asymptotes for the tangent function. And then in terms of evaluating, kind of the same idea there. Tangent of tangent inverse of x is x, so those functions will undo each other as long as x is any real number, because tangent inverse has a domain of all reals. But when we find tangent inverse of tangent of x, that x value has to be between -pi/2 and pi/2. So if we're looking at an x value outside that window, we would have to find an angle that is equivalent somewhere in that window so that we can evaluate it. So now if we want to start actually evaluating or finding values of the inverse sine function, take a look at A here, sine inverse of 1/2. The way I think about it is that's really asking the question, similar to what we've already been doing, is sine of what angle, sine of what number, where x is an angle, is equal to 1/2. So we've already been solving equations like this for the last couple days in 9.4. So really when we are evaluating the inverse sine, or at least right at the beginning here, we're basically asking ourselves, sine of what angle gives me 1/2? That's what inverse sine of 1/2 is really saying. The only difference here is our angle has to be between -pi/2 and pi/2. So we think about what our solutions would be in general for that equation, sine of x equals 1/2. I'd have two. I'd have pi/6 and 5pi/6. But because only pi/6 is in the window, -pi/2 to pi/2, that is our only solution there. And every other answer where sine of x is 1/2, every other angle would be outside of that interval, -pi/2 to pi/2, so that's the only solution. So if you look at part B, similarly, where is sine inverse, what is the value of sine inverse of -1/2? So sine inverse of -1/2, it's really asking you sine of what angle is -1/2. So what I drew here is -1/2 is between -1 and 1, which is the domain of sine inverse, so can be evaluated. So what are the angles that give me that? In general, if we were doing this the other day, we would say, well, 11pi/6, that's somewhere between 0 and 2 pi. The difference here is my answer, my angle, has to be between -pi/2 and pi/2. So 11pi/6, although is in the right location, thinking of where it is on the unit circle, it's not the angle that I want. So I'm going to draw a unit circle here and hopefully highlight kind of what's happening here. So if I look at 11pi/6, it'd be right there. It'd be rotating almost all the way around the circle and stopping just short of the x-axis again. That's 11pi/6. But if I want my solutions to be somewhere between -pi/2 and pi/2, I still want to be in that same location because sine is -1/2 there. But I want the angle, which would be rotating backwards, pi/6. So sine inverse of -1/2 is actually negative pi over 6, and negative pi over 6 would be the angle that is between negative pi over 2 and pi over 2. So we have to think about our solutions in terms of what the possible answers are for sine inverse, and that will kind of dictate how we approach finding those values. So we want to look at example 2 here, a few more problems that we want to find the values of. Still going to kind of approach it the same way. The only difference here is we're going to be kind of composing sine and sine inverse and trying to see what's happening here. So if you look at part A, sine inverse of sine of pi over 4. So if I look at pi over 4 as an input for sine, it has to be somewhere between negative pi over 2 and pi over 2. That's the domain of my sine graph. I'm restricting sine to only that window, and because pi over 4 is in that interval, negative pi over 2 to pi over 2, sine inverse and sine will essentially undo one another, which means my answer should be just pi over 4. And you could verify that by finding sine of pi over 4, which is root 2 over 2, and then finding sine inverse of that, which should still give you the angle pi over 4. So if my value on the inside is something that I can evaluate, and I have sine inverse of sine, those functions are essentially going to undo one another, and I'll be left with whatever that value was. So if you look at part B, here's the difference here. I kind of approach this differently in class, but I do want to address that this is something you can evaluate. So there is kind of an additional thing we have to consider. So sine inverse of sine of 2. 2 as an angle, remember angle in radians, is not in the interval negative pi over 2 to pi over 2. So where is it, right? If I kind of draw a picture, 2 radians is somewhere in quadrant 2. So it's 1 radian is about 57 degrees-ish. So 2 radians would be, 114 or somewhere in quadrant 2. So that angle is not in my interval negative pi over 2 to pi over 2. But I can find an angle that is in quadrant 1 that has the same sine value. So how would I do that? So again, that angle is 2, but I want to be between negative pi over 2 to pi over 2. So if I look at this angle right there, so draw one in quadrant 1, those should have the same sine value, meaning they're the same distance up the unit circle. But how do I find out what that angle actually is? Well, if I took pi, which is halfway around the circle, and subtracted 2, which was my original angle, that would give me that angle right there in quadrant 1. So the angle would be basically half a rotation and then back up 2 would be an angle in quadrant 1 that has the same sine value. So how do I find that the value of this original problem, sine inverse of sine of 2? I'd have to rewrite it as sine inverse of sine of pi minus 2. And the reason I would do that is because pi minus 2 as an angle is between negative pi over 2 and pi over 2, and that is something that I can evaluate. So in this case, because now I have an angle where sine is defined, sine inverse of sine of pi minus 2 would just be pi minus 2. So the process here would be, if it's not something that I can evaluate, see if I can rewrite it as something that would have the same value so that I can use the property that sine and sine inverse are functions that undo one another. Now, if we look at C, sine of sine inverse of 2. 2 is not in the interval negative 1 to 1. Okay, because now sine inverse is on the inside of this composition. Now here's the problem. I actually can't rewrite sine inverse of 2 so that it is it is something that can be evaluated, because sine inverse is only defined from negative 1 to 1 and never defined outside of that, which means 2 is not something I can rewrite in a way that would be defined. So therefore, sine of sine inverse of 2 is undefined. There's nothing I can do to rewrite that. There's no equivalent value I can do. The difference between C and B is in B we're looking at an angle, and there's symmetry on the unit circle where I can rewrite it, whereas in C, the input for sine inverse is value between negative 1 and 1, and that's never something that I can evaluate. So that one would be undefined. And then if you look at D, sine of sine inverse of negative 1 over root 5, what I have to consider here is negative 1 over root 5 in my domain of sine inverse. And again, my domain of sine inverse is negative 1 to 1. So is negative 1 over root 5 between negative 1 and 1? And it is, which means sine of sine inverse of that value would just be that value. So again, using the property that sine and sine inverse undo one another is really useful, but I do have to check and make sure that what I'm evaluating on the inside is in my domain so that I can use that property. So moving on to example 3. So look at part A, cosine inverse of 0. The way that I'm thinking about that problem is really asking me cosine of what angle equals 0. So again, you don't have to rewrite it this way, but the reason I would is because cosine of x equals 0 is something kind of we've been solving. So if you rewrite it that way, it's often easier to kind of see what the answers should be. But cosine inverse of 0 is essentially asking you what angle between 0 and pi, because that's our restriction for cosine, or cosine inverse, what angle between 0 and pi makes this true? Or what angle between 0 and pi is cosine inverse of 0? So the angle, the only angle in the interval 0 to pi where cosine is 0 is pi over 2. Now there are other angles like 3 pi over 2, 5 pi over 2, 7 pi over 2 where cosine is 0, but I'm only restricting my answers to within the interval 0 to pi because that's where cosine inverse is defined. That's the potential output for cosine inverse. Now if we look at B, cosine of arc cosine of 2/3, that's really asking cosine of cosine inverse because arc cosine is just another way to write it. How do we find this? So looking from the inside out, is 2/3 in the interval or in the domain for arc cosine? So remember, the possible domain of arc cosine is negative 1 to 1. So is 2/3 in that interval? The answer is yes, which means cosine of arc cosine of 2/3 would be 2/3. So you're essentially checking to see if you can basically use the property that cosine and arc cosine are inverse functions of one another, which means they undo one another. But I do have to check to make sure 2/3 is something that is in my domain for arc cosine. And then for C, I want to clarify kind of how to approach this. So arc cosine of 4. And now if you look at what's on the inside is cosine, which means I'm only going to look at values between 0 and pi. And 4, as a radian measure, as an angle, is bigger than pi. Remember, pi is like 3.14 something. 4 is bigger than that, which means that's in quadrant 3, and I'm only looking for angles in quadrants 1 and 2. So if I think about the circle here, call that 4 radians approximately, there is another angle in quadrant 2 that has the same cosine value. So the way you'd find that is, I'd basically have to figure out what that angle is, which if you look at where those two angles touch the unit circle, they would have the same x value or the same cosine value. So how do I find that angle? Well, if I go 1 revolution, which is 2 pi, and then back up 4, that would take me to the angle in quadrant 2. So 2 pi minus 4 would be the angle in quadrant 2 that has the same cosine as 4. So now I can rewrite this problem as arc cosine of 2 pi minus 4, because 2 pi minus 4 is now as an angle in my interval 0 to pi, which means arc cosine of 2 pi minus 4 would just be 2 pi minus 4. So the process here is, if it, specifically for when the interior is cosine or sine or tangent, if that angle is outside my restriction, then I have to try and find another angle that is within my window so that I can evaluate. So that's what I had to do to find 2 pi minus 4. So moving on to example 4, now we're going to be looking at values for tangent. So tangent inverse of negative 1 is really asking the question, tangent of what angle equals negative 1? And now you don't have to rewrite it like that, but the reason I am, at least for today, is so that we can see that we've really been solving equations like this. We just haven't been putting this inverse notation on it. So for what angle is tangent negative 1? And I need the angle to be between negative pi over 2 and pi over 2, because that's where we're restricting our tangent function when we are evaluating the inverse tangent function. So Tangent is negative in quadrants 2 and quadrants 4. So I'm going to be looking in quadrant 4, but I need an angle in quadrant 4. Think about it, an angle in quadrant 4 that is between negative pi over 2 and pi over 2, which means if I want to find that angle, I would have to start at 0 and rotate backwards to where 7 pi over 4 is, but I'm going in a negative direction. That's rotating negative pi over 4. So the angle for which tangent is negative 1 that's in quadrant 4 is negative pi over 4 because that has to be between negative pi over 2 and pi over 2. Now you don't have to rewrite it this way. You can really think tangent inverse of negative 1 puts me in quadrant 4, and I need an angle in quadrant 4 that's less than pi over 2, greater than negative pi over 2, and that would be negative pi over 4. And then for part B, tangent of tangent inverse of root 5. What I have to think about is what is the domain of tangent inverse? So remember when we looked at the picture, we think about what the range is of tangent, it's negative infinity to infinity. So because root 5 is a real number, that means tangent inverse of root 5 exists, and then I would just use the property that tangent of tangent inverse of a number is that number as long as tangent inverse is defined there, which tangent inverse is defined everywhere. So my answer here would just be root 5. Now if you look at example 5, we're going to be looking at a few problems that are slightly different, and you'll notice if you look specifically at B and C, we're going to be finding a composition of functions, but they're not going to be like sine and arcsine or cosine and arccosine. It's going to be a composition of two different functions. But for part A, we're kind of going to approach this the way we have been, which is arc cosine of 5 pi over 2. My first thought is going to be, is 5 pi over 2 between 0 and pi? And hopefully we'll say no there, which means I need to rewrite that angle as an angle that's in the same place, but is between 0 and pi. So think about it, 5 pi over 2 would be one full revolution and then up to pi over 2, which means I can rewrite this as arc cosine of pi over 2. Because cosine of 5 pi over 2 and cosine of pi over 2 have the same value. So now, arc cosine of pi over 2, those two functions will undo one another since they are inverses, which means my answer would just be pi over 2. Now if you look at part B, like I said, sine of tangent inverse of negative 1, the way we're going to evaluate this when the functions are not inverses of one another, so sine and tangent inverse, it's not like those can undo one another, is you're going to work inside to outside like you would in any composition of functions. So the first thing I'm going to find is tangent inverse of negative 1, which is negative pi over 4. So what this problem becomes is sine of tangent inverse of negative 1 is really going to be sine of negative pi over 4. So then sine of negative pi over 4 would put me in quadrant 4. Sine of that angle would be negative root 2 over 2. So when you're composing two functions that aren't inverses of one another, you work your way from inside to outside to find the value. Part C is one that will require a little bit of connection to a previous chapter, and that is this. Cosine of arcsine of 2/7. The first thing you should think about is 2/7 is not a value we know. Meaning, when I say a value we know, I mean like root 3 over 2, or 1/2, or 0, or root 2 over 2, essentially a value for sine. So 2/7 is not one that we know, it's not one that appears on a unit circle. So what I'm going to think about is there a way I can draw a reference triangle to match the context for arcsine of 2/7? So again, here's how I'm thinking about it. Arcsine of 2/7 is basically asking what is the angle where sine is 2 over 7. So I can kind of think of that as a generic angle and draw a triangle. So arcsine is only going to exist between negative pi over 2 and pi over 2 in terms of its range. So therefore, if I think about where this triangle would be, it'd be in quadrant 1 or quadrant 4. And because sine is positive, 2/7, I'm going to draw a triangle in quadrant 1. So my triangle would look like this. Theta would be whatever that angle is that gives me a sine of 2/7. And since sine is opposite over hypotenuse, I have this triangle here. Opposite is 2, hypotenuse is 7. So really, arcsine of 2/7 is giving me this triangle where the angle is something I don't know. Okay, again, I'm going to call it a generic angle. So now if I think about the problem or the original problem I was trying to evaluate, cosine of arc sine of 2/7 is really asking me for cosine of the angle that gives me this triangle. And again, I don't know what the angle is, but I have now a triangle, a context for which I can evaluate cosine. So in order for me to evaluate cosine, which is adjacent over hypotenuse, I would need to find the adjacent side, which in this case, if I use the Pythagorean theorem, would be 3 root 5. So that means the adjacent side is 3 root 5, and if I want to find cosine of theta, again, where theta was the arc sine of 2/7, it was the angle that gave me this reference triangle, it would be 3 root 5 over 7. And problems like that where, again, the 2/7 was something that we didn't recognize from the unit circle, so I'd have to draw a triangle that shows that the sine of whatever that angle is 2/7, and then use that triangle to find the value of the outer function. Again, that outer function could have been tangent, cotangent, secant, cosecant, could have been any of the other trig functions where I'd be using this triangle to evaluate it.